Let's take a trip back to Calc 1. Hopefully this looks familiar to you from your calculus past. When we were in Calc 1, we were interested in answering the question, what is the area underneath a curve? And we started off thinking about that by approximating that area with rectangles. And we said that the approximation would get better and better and better as we got more rectangles underneath the curve. So we would calculate the length times width for the area of each rectangle. And then we said, as we get more and more rectangles, this approximation would get better and better. By the time I get over 200 rectangles, then this was a really good approximation of the area underneath the curve. We can hardly tell the difference between the rectangles and the actual area underneath the curve. But rather than calculate all of those rectangles, we found that the integral would calculate the exact area underneath the curve for us. But it's important to think back to those rectangles, because those rectangles, that f of x dx, the f of x was the height of all of those rectangles, and the dx was that really teeny tiny width of all of these little bitty slices of rectangles across this area. This is the second applet that I have posted on our Moodle page. It's the R3 version of what we were just looking at. Instead of approximating area underneath a curve with rectangles, though, we're going to approximate volume underneath a surface with rectangular prisms. All right, instead of slicing up the x-axis and then building rectangles that are the height of the function, I'm going to slice up the xy plane into a grid. All right, and then we're going to build rectangular prisms out of that have their heights determined by this surface. And you can see that this would approximate the volume that would be trapped underneath this surface. It's not a very good approximation, but like in R2, all we have to do is increase the number of rectangular prisms that we have. So I have a slider up here. This applet is a little more complicated than the other one, so it's a bit more laggy. All right, but as we increase the number of rectangular prisms, as we decrease the size of those little grid slices on the XY plane, you can get a better and better approximation of the volume underneath the surface by doing this with more and more rectangular prisms. So we know from Calc 1 that we can calculate the exact area underneath a curve with a definite integral. But the parts of a definite integral have their roots in these rectangular slices. So that f of x dx is really the length times width area calculation for each one of those little bitty slices. So the f of x gives you the length or the height of these rectangles as you go along the function. This is our length. And then the dx, that's the width of those little bitty slices. All right, and so length times width for each one of those little rectangles would give you the area of the rectangle. And then the integral is a way of adding all of those little rectangular areas up. So we add them up with an integral. So you may have guessed by the title of this section that those double integrals we've been calculating are going to calculate volume underneath the surface for us, and they are. But just like the guts of the single integral came from length times width area calculation, the guts of the double integral come from length times width times height volume calculations for those rectangular prisms. So just like the area calculation, the function value is going to give you the height of that rectangular prism. So we're going to call this the height of each one of those rectangles. And then the dx dy, think of that grid that I had on the xy plane on the applet. That's going to give you the length times width of one of those little rectangular slices. All right, so one of these is going to be the length and one of them is going to be the width. And it doesn't really matter which one you think of as length and width. Length times width times height gives you volume. All right, and because it doesn't matter which of the dx or dy is the length or the width down there, however you want to think about it, we're going to start to refer to this dx dy bit at the end as dA, where A is some area slice of the xy plane. So here in the middle of the slide, you can see a sort of shorthand notation for our double integrals. I mentioned the dA at the end. This can either mean dx dy or dy dx, depending upon whichever is more convenient for the integral that you're working on. And then the double integral has an R underneath it. That means a region, it stands for region, of the xy plane. All right, and that could be a rectangular region where we have those constant limits on the integral. It could be referring to a differently shaped region of the xy plane. We've seen lots of that in the last section. All right, but this double integral is going to give you what we call the signed volume under z equals f of xy over a region R in the xy plane. Okay, so what does signed volume mean? You ran across a similar thing in Calc 1 when you learned about area underneath a curve. So if I give you a curve, and I ask you to find the area between 0 and 5, you know, this would calculate the area that's trapped between the curve and the x-axis. So like it would calculate this area, and then it would also calculate this area up until it got to 5. And it would treat the stuff above the x-axis as positive area and the stuff below the x-axis as negative area. The double integral is going to do the same thing in R3. It's going to call volume that's above the xy plane positive volume. Any volume that's hanging down below the xy plane, it's going to call negative volume.